we're just doing a few different examples of those damp springs that are going to represent those three different cases we talked about. So the first one is going to be that we'll think about d2, I'm going to actually do the double prime notation because that's less messy for me, x double prime plus 2x prime plus 10x equal to 0. And what that's going to give us is if x is equal to e to the mt, x prime equal to m squared e to the mt, and oops, that was just m, and x double prime equal to m squared e to the mt, then we're going to end up at 0 equal to m squared e to the mt plus 2m e to the mt plus 10 e to the mt, our differential equation, or m squared plus 2m plus 10 all times e to the mt. And when we solve, 0 equal to m squared plus 2m plus 10. When we get 0 equal to m squared plus 2m plus 10, we have to solve that using our quadratic equation. We're going to get m equal to minus 2, plus or minus square root 2 squared minus 4 times 10 all over 2. Going through this process to get to this quadratic equation is another thing where like the steps between are more important. If you go from this equation and then look at this and just jump right there and plug in that formula, that's not demonstrating knowledge of this type of problem. So please don't do that. So let's see, minus 2 plus or minus the square root of 4 minus 40 is negative 36 over 2. So that's just going to be minus 1 plus or minus 6i over 2. So that's just minus 1 plus or minus 3i. And so we just remember we did these rules all the way back here. But if m is equal to alpha plus or minus beta I, we're going to do e to the alpha cosine beta x, e to the alpha sine beta x. So we have m is equal to alpha plus or minus beta I for alpha equal to minus 1 and beta equal to 3 is going to give us x of t is c1 e to the alpha, so minus 1 times t, times cosine of beta, 3 times t, plus c2 e to the minus 1 times t, sine of beta, 3 times t. And then something that's going to help us kind of see what's happening here is just to pull out that common e to the minus t term. And then that's just e to the minus t times c1 cosine 3t plus c2 sine 3t. So that's our solution. And the reason I pulled it out like that is so that we can see that kind of this part right here is our damping. It's going to be taking things and sort of making them do this over time. And this part right here is our oscillation. It's going to take things and make them do kind of this over time. And so put together, what we're going to get is solutions that look kind of like this. Here's time, here's x. And we want sort of to damp things down over time from that exponent. But the oscillation means that we're going to be kind of wiggling within that band. And that's what a solution will look like. And so when we have sort of a softer balance between lambda and omega, so that is when the damping coefficient is sufficiently small that the spring coefficient causes this less than 0 in our discriminant of the roots, we get this outcome where you've got this damped oscillation that kind of gradually dies down. Our second example is going to look at sort of the opposite of that. So we're going to look at x double prime plus 5x prime plus 4x equal to 0. Again, when we have our x equal to e to the mx, we have x prime equal to m e to the mx, and x double prime equal to m squared e to the mx. Our ODE becomes 0 equal to m squared e to the mx plus 5m e to the mx plus 4 e to the mx. And we factor out that e to the mx that we don't need. And the auxiliary equation becomes zero equal to m squared plus 5m plus 4. Okay, and then that one we can go ahead and just factor. M plus 4 times m plus 1 will give us m squared plus m plus 4m is 5m plus 4. And so that checks out. And so we just have two real numbers, m equal to minus 4 and m equal to minus 1. That's that second case we said was possible. Sort of the, if we had used the quadratic equation here, the thing inside the square root would be a real number, and then everything simplifies down to two real numbers. And so the solution is x equal to c1 e to the minus 4t plus c2 e to the minus 1t. And what's happening is that both of these solutions, both parts of the solution are just damping. That's an exponential, just bringing things down over time. That's an exponential, just bringing things down over time. The only thing is there's a little bit of like texture to the fact that they have different arguments, so they kind of are decaying at slightly different rates. But if that's our t and that's our x, kind of all that can happen is maybe something like this, where you might have a little hump at the start, or you could head down a little more smoothly, but it's kind of like that. And so this is like a severely damped system. This 5 right here is really big, and so that's why our roots are both real numbers, and our 5 is related to that beta coefficient. So what we're saying is that the damping is very strong in this system. And then I sure hope I have enough time. Yeah, okay, we can do our last example as well. So our last example is going to be that one that switches between these two. So we've got x double prime plus 8x prime plus 16x equal to 0. And we take x equal to e to the mx. Oops, I hope I didn't do that on the last one. I did. Those should have all been t's. If we were in class, I bet you all would have said, like, as soon as that happened, oh no, why are there x's? And I would have said, oh no, there shouldn't be. And you would have had a chance to fix it right then instead of having to go back and fix it all at once right now. I'm sorry. But I did it right on the first one. So x is equal to e to the mt, x prime is m e to the mt, and x double prime is m squared e to the mt. When we plug it into our differential equation, we get m squared e to the mt plus 8m e to the mt plus 16 e to the mt. And again, you're going to get really tired of doing this, but since it's, such a, numerical and straightforward method, I think you'll actually appreciate that you get to do it so much. But you factor out that e to the mt so that we can be left with our auxiliary equation is 0 equal to m squared plus 8m plus 16. And then this is again the type of equation that we don't have to solve with the quadratic equation because we can just factor it. M plus 4 times m plus 4 gives us 4 times 4 is 16, and 4 plus 4 is 8. So that's how you factor this equation. And we have m equal to minus 4 repeated. So our solution is going to be x of t equal to c1 e to the minus 4t. And then we use that first special rule we discussed, c2 t e to the minus 4t, to deal with the fact that our root is repeated. And that would be our solution to this problem. But what we're doing here is talking a little bit about the behavior of each. So for this one, you've got your regular damping term here. But this term is going to kind of have the opportunity to climb up and then climb back down because of that t up in front. So when we plot it against time, what's going to happen is you get solutions kind of like this. This is sort of the critical breaking point between those other two cases we discussed.